So this is my nephew, Tim, who's now a dad. That's his little baby girl, Wyota. Tim and Wyota. So I'm like a grandpa. This is my grand niece. This is my third grand like nephew or niece. So my sister Susan's daughter Kirsty has two babies, and now Tim has his first. And they live in Australia right now. Tim and Marika, Wyota's parents, they live in this mining town in Australia where the goal is to work there like a year or two and you make a lot of money, but it's a super hot place to live. You only can work at night stuff, but you try to stash all of that money and then you can go like buy a house, like half a house, and then get a job. They want to move back to New Zealand. That's where Marika's from, and Tim's kind of New Zealand, California, because my sister married a Kiwi, so they live out in New Zealand. And Wyota is a Maori name. They're like the natives of New Zealand. It means pure water, so it's like a nice thing, like pure water is healthy, it's life, pure ocean water, things like that. And look at the Australian waters are nice, clear. So, oh yeah, here's a close-up of Wyota, so cute. And here she is, another one with my daughter, Michaela, knitted this turtle for her. She got into knitting, crocheted, not knitting. Okay, so today we'll do this intro and then chapter 1, we'll keep going on that. And again, it's a great idea to click through these outlines to see what we're up to each week, and as we go through things, I'll clear things up in these. So spectroscopy assignment summary, about clearing things up. So I had these all like kind of confused with the pre-labs and all that. So let me make it really clear. So I have a link here. I made this Google sheet that explains them hopefully better than I had before. So there's 5 different assignments actually I've made for learning how to use the NMR and the IR. And they're worth a lot of points, 80 points. It's like approaching an exam material amount of points. And you should be able to get them all. Just turn them in on time, answer all the questions. Questions are all pretty straightforward. So then, so the how to use our IR spectrometer, that's the first one. I decided to have that one to do first. I made a pre-lab out of it to start it, and then the actual assignments here. So that one, some people have finished it. Let me see, how many have finished that one so far? That one is not due till the 7th. I could have made that due date earlier now that I'm seeing how long it's taking some people, but I'll keep it where it is. I'm not going to make it earlier at this point. But how many of you have finished that one?
I have.
I hear one. You could put it in the chat if you finished it. Almost like 5 questions. Like, cool. All right, good. So if you haven't made a lot of progress on that, besides the first couple questions from the pre-lab, really get moving on that. And you'll be able to do it in lab as well, but you should do it outside of lab just to get it going. And then the spectroscopy intro. Oh wait, so let me go back a little bit. So this how to use our IR spectrometer. It's a due dates here, and then it's 15 pages, not as long as some of the other ones. It's got 4 animations, the Google slide animations, just 1 video. So that one's not too long. The spectroscopy intro, that's the longest one. This one goes through and explains how NMR and IR work, how to look at their spectra. And so it's not due till the 13th, the pre-lab. This was the confusing. I didn't have this initially as a pre-lab, correct, but now it is. But it's okay I'm not even going to worry about whether people did this pre-lab because I was all confused on that. But what I want you to do is to do this, keep working on this in lab and outside of lab. Try to get it done because it's long with 78 pages, 23 animations. I couldn't believe I counted them all. I'm like, oh, this took me forever to make, but I think it's good. And there's a lot of videos. And again, if you're going through these and the videos are long, you could on YouTube, you could 1.5 times the speed or double the speed if you're comfortable with that. Nope. And then how to use our NMR spectrometer. This is the document which talks you through how we actually use our machine, how the commands we use, like putting the sample in the machine, first taking the proton NMR, doing different things. So, and this is what I'll be training the Thursday, tomorrow. I'll start training people on this. And so if you can, you probably won't be done with this one by tomorrow. I don't think anybody will, but if you want, you can it's logical to finish this one and then start the how to use our NMR. But if you want to peek ahead, you can, just to get an idea. And I'll be verbally teaching you that in lab when I teach you how to use the instrument. And then I have a workshop here. What this is, it's just a lot of NMR and IR practice problems. So you get really good at understanding how to read the spectra. And it'll have like an unknown molecule where you have the IR spectrum, proton NMR, carbon NMR, and then just with those, and I give you the molecular formula, you have to figure out what the molecule is, and you'll get good at it. It's kind of fun, they're like puzzles. And then finally, the experiment portion of this whole thing is you are going to get an unknown molecule, and you're going to get the IR spectrum of it, and then the proton NMR and the carbon NMR. And then you're going to figure out the structure of it. And then you're going to be partnered up with 2 other people, and they're going to take spectra of their unknowns and share it with you. So you'll have 3 unknowns to figure out. And so we'll be doing this for a while. This one, you'll see it has a really late due date. The reason why is we only have 1 NMR. And when you first learn how to use the NMR, you're kind of slow at it. So I give us plenty of time for people to get on the NMR. What we'll be doing in lab is we'll start other experiments. Like the next experiment is solubility of organic compounds. We're going to be starting that, but as most of the class is working on that, one or two of you can go over to the NMR, be working on it, and then when you're done, go back and work on solubility. And people go. So we have like the NMR experiment kind of happening underneath the other experiments, because it just takes a while to get used to using the instrument. Okay, any questions about that? What? It's still the wrong color. I need it darker. I think I have to go one more higher. There we go. Okay, so all right, we got a couple people doing good. Okay, and then the next thing I want to talk about is to prepare for today's lab. So since we had the Monday off, things are out of whack a little bit between the Monday, Wednesday lab section and the Tuesday, Thursday lab section, but we'll get back on track. So here we go. So come with your green pass course, bond line, structure, drawing skills. So you're going to take this quiz that you were going to take Monday. You're going to take that today, the Wednesday lab people. And the counting secret hydrogens quiz, you're going to take that today because you missed it on Monday. And then you're supposed to be taking the functional group quiz today because you would have done these other 2 on Monday. But if you want, instead of having 3 quizzes today, you can postpone that till Monday if you like. And actually, maybe I'll have, it's up to you. If you want to take it today, you can. But if there's only a couple people want to take it today, I don't want to like have everybody have to wait for that, unless I can put them off or something. We'll figure it out. So if you want to just have these 2, that's good enough. And then computing devices with the internet, like I said before, have these things. So when I'm training a group on the IR, the other people can be working on their other spectroscopy assignments. And then bring goggles. UVEX are good. And lab coats are not required, but you can bring them if you like. Then and then we're going to be checking into lab on checking into lockers this day. Yeah. And then Thursday, they're doing a little bit different, green pass. And now Thursday, you will have the functional quiz. I don't want to do this. Sorry, because you already had the other 2 quizzes. So you're going to do that quiz on Thursday. Functional group quiz, and then computing devices, blah, 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 goggles. There we go. Okay, so now more extra credit. I already mentioned this before, but remember, if you come to an office hour, you can get an extra credit point. So come on by. Tomorrow I have office hour, 9 to 10. Stay for a while, work on the Jamboards. Yesterday I had about 5 of them, 5 people in there, and then they were working on the quiz that they wanted. Some of them took yesterday, others will take today. And so when they were working through the quizzes with me, there was these key little mistakes they were making, which I'm like, oh, let's fix that. And then they're, oh, now I get it. So when they take the quiz, they get full credit. But it's not just the points. It's like now their bond drawings, they're seeing things in 3D, and their line bond drawing skills are so much better. It's going to just help understand lectures and everything. Okay, more extra credit. You can come to if you come to my live lectures, like all of you here, like I see Inna and Carly and the rest of you, you can get extra credit. So go into the assignments area, extra credit, and tell me you were here today, and I'll give you a point, up to 5 points, I think I said. Okay, yeah, so few people told me they were at Monday's lecture, and I gave them extra credit. And then those of you who were at Mondays, I know there was more in the Monday lecture time than I got requested extra credit from. Go ahead and go into Canvas and do that, get some points. And I talked about this before, extra credit can only help you, it can't hurt you. Even if you don't do any extra credit, it might change your grade up. Okay, now homework due dates, I mentioned this before, is just real quick. I'll set the homework due date when we're done with the chapter or the chapters that it requires in lecture like this. So I haven't set homework, chapter 1 homework or homework A, which just covers chapter 1. I haven't set the due date yet because we're not done with chapter 1 yet. Okay, and then just make sure you attempt them all. I'm gonna grade them quick. It's like they're working, they're trying, done. Okay, initial due dates. Yeah, if you could turn in things a little late, there's the due dates there. Oh, and I kind of fixed up these due dates. I think they're better now, like week 1, week 2. You know what? I should have. I still want to change this. I have like 2 different things going on here. I'll show you what I mean. In my, I kind of make my life difficult when I do this. Like my organic chem step by step, I have this, and then I have a due dates, and then I have things all over the place. But I'm trying to make them all the same, so it's helpful to have stuff in multiple areas. But this is looking much better now. So, for example, we're in week 2, and our assignments now. I have everything. I have all 5 of the spectroscopy assignments listed with their due dates now, so you know that you could click into those. And then on week 3, I got them again. And then in week 4, I lose the IR thing because it was already due. So I'm trying to get more organized for you. And close out. Oh, that's fine. So in week 2, lecture outline Wednesday. No, outline. Okay, got that. And then remember goggles, bring your goggles, please. Honors tryout. So I offer honors contracts each semester, and they're good. They give you more practice at what we're doing. And I try to set up the honors so that when you're doing your honors project, it's not like a totally different thing than your exams and what we're learning in class. So if you're an honors student and you can do it, then it's going to take you some time, but as the things that you're working on, your honors project is going to help with the next exam. So it's not like completely separate, because I know you as science majors probably have physics, math, biology, or whatever. You just have so much going on. It's not like you want to take a honors contract that's completely separate from the normal class. So normally I usually have about 4 to 5 students. And then we usually make these animations. That's what we do most of the time. And let me pause real quick. I got some chat here. Would that be the 13th? Because next Monday is Labor Day. Raphael's asking me about the due dates. So the due dates are kind of weird because, like, normally when I have in-person lecture, I can make something due on a lecture day that everybody attends. But now that I have 2 lab sections, if something's due, if I want to make something due in lab, it'll be due like for the Monday, Wednesday people and Monday, if say it's due on a Monday. And then the Tuesday, Thursday people, it would be Tuesday. So when I go into Canvas and I set a due date, if I set it for Monday, the people on Tuesday, Thursday, it's like, oh, it's going to be late for me. If I set it for Tuesday, the Monday people will say, well, oh, I don't have to do it. It's not due Monday. I'm like, So, and with due dates, I make them so that if they're 4 days late, no points off. So yeah, don't worry about that, Raphael. You could turn that in on the 13th. Yeah, it does. Yeah, it doesn't. You could turn it in on Labor Day if you wanted to upload it to Canvas, but you can turn it in paper there. So yeah, should we wait until we have made it 5 days of lecture and say 5 days? Oh, you can do it either way, Carson. For the extra credit for attending lecture, you can do them all at once, or you can do them one at a time. Spell needed. I don't know
Yeah, on this, I think it's the previous slide.
Oh, it's a spelling typo.
Mhm. Yes, sir.
Okay.
Uh, yes.
Well, I don't know.
It's on the second sentence.
Okay, after I finish covering the material that is needed. Okay. Thanks. All right, back at it. So honors. So I normally have 4 or 5 of you a semester who do this, and so in the first year I offered honors, I got talked into it by a biology professor, Elena Pravasudica, but she's moved on to, I think she's at University of Nevada now. But so she talked me into giving an honors contract, and I go, okay, I'll try it. And then so I just said to the class, hey, if anybody wants to do honors, they can. So like 15, 20 people said, oh, I'll do it. But then almost all of them got too busy with the semester, and they wound up like causing me a lot of work with me having to say, hey, did you do the first thing? Did you do the, it was like, it was too much going on. So then I got smart. The next year I did a tryout, and that's what I'll do. I've done since. So I have a tryout, and the tryout's not meant to be something that like stops you from making it. It's basically something to test whether you have the time in your schedule to do this. So if you can't find time in the next week to do the tryout, that probably means the rest of the semester you're not going to have time to do the projects, and that's okay. You don't have to do it. It's just something extra. So if you want to do honors, you have to do this tryout and turn it in by a week from today, the 8th. And you can turn it early too. So it's due next Wednesday. And if you find time in this week to do it and you want to do honors, then you probably will be able to do it. It's not one of those things where, oh, they have to get over 90% correct on it. It's not like that. You have to make an attempt. So this is the honors tryout. You're going to read about this thing called absolute configurations. It's a stereochem concept. We're going to learn about it later, but you'll have to do it a little ahead of time. Just a little exercise. See if you could like teach yourself this and then complete the assignment. So so you'll look it up online. There's lots of videos and resources on how to do this. This is one of the common organic chemistry operations that everybody who takes Ocam learns. So here's the tryout. You're going to determine these 1, 2, 4, 6, 8, 9 molecules. You'll determine if their absolute configuration is R and S, and you have to figure out what is absolute configuration, all that. And then lastly, you'll make up another 5 molecules and assign R and S to them. So yep, if you're interested in honors, do that. And oh, and I'll show you what honors students are going to do. We have our list of animations, right? Up here, animations. So this is like where I store all the animations I've made. And then this is sheet 1. See how it says sheet 1 right there? Then sheet 2 is next door. And these are animations that were made by honor students from the past. So let's check out Monpreet's here. Yeah, this is pretty good. I'll just click through it really quick. So this was her first animation. It's for pKa's and predicting acid base, and she made it fun. She got a theme. It's got some SpongeBob and Squidward talking about it. Here's the values. And so she made all this where she's doing it all these curve notes and stuff. And so it's time consuming, especially at first. But as she's doing it, she is really getting these concepts because it makes you really slow down and think about the curved arrows and the pKa's and predicting the product, whether product or reactant favored. So, and there's other ones there. And these are also resources now for you. So when we go to, soon we're going to learn about acid-base chemistry and this stuff. And so you have all these animations. Got Rob Tage here. Let's see what hers looks like. What theme does she have? She had some muscle themes. Okay, and then when we learned about the SO2 mechanism, we got all the different animations. You can practice this. Rule of 13, this is for mass spec. Markovnikov hydration of alkenes. Got all these. And got more. And so this year, you honor students this year will be adding to this list of animations. So it's an honors project that helps the honors student get honors and also learn the material well, but it helps the class because now it's a resource for the class. Okay. And then key links for the fall for this semester. I talked about that before. Just to remind you, there is a link to keys, answer keys, like homework 1, the first homework assignment, answer keys up there for most of the problems. And then no lecture on Monday because that's Labor Day, the 6th. So what was the 13th? Is there no class on the 12th? I don't know. So no Monday, no lab, no lecture, no lab, but Tuesday there will be a lab, and I'll have a basic skills worksheet that I'll give out at the Tuesday lab section, but I'm also going to give it to the Monday, Wednesday people. It'll be a relatively easy assignment, and it'll be something that can be worked on along with spectroscopy and all the other things. And also during this Tuesday lab period, we can train on the NMR and IR, do some lab work as well. And then the Monday, Wednesday lab students, I've decided I'll let you come to the Tuesday lab if you want. Normally, that's what I always do when we have like a lab that's missed, another lab section. So, and I usually don't get too many. So if I don't, I think it'll be okay because I have 2 lab sections on Tuesday. There's a 10:45 to 1:50 and then 2 to 5:05. So Monday, Wednesday lab students, if you have openings in these times, you can come and join in on the trainings or work on problems or whatever. Just do the normal, wear the mask and get the green pass. And then Monday is the add drop full refund deadline. So if you're feeling like by Monday, this Monday, that, oh, this is just too much, then, and you have like, say you have organic, physics, bio, calculus, you're finding out this is too much, then go ahead and drop, like math or physics or bio. You don't drop Ocam, but drop those other ones so you have more time for Ocam. Just kidding. No, it's up to you, whatever you do. But if you try to drop after the 6th, you won't get your money back. All right. So I like my Sierra College email much more than the Canvas message app. And I know some teachers say, oh, always message me in the Canvas app. I'm the opposite. I would rather you message me in the Sierra email. It's much easier for me to use that one because I can like cut and paste things a lot easier. And the Messenger app, the message app in Canvas, the font is like 6. And I'm always like, what does it say there? It's weird. So, but I mean, if you message me in that app, no problem, I'll respond. But it helps me to message in the other one. All right, now we have another SO2W, Student of the Week. The Student of the Week this week is a Viking from Oakmont, a bio major. Will transfer to Howard University in Washington, D.C., the famous Howard University. Will become an anesthesiologist. Will be putting you on the brink of death, sleep and death right there, holding you on the line. And played soccer and track. I don't know what that dot is, that's bugging me. So athlete in high school, soccer and track. Been to 10 countries. Born in the USA, but parents are from Nigeria. Middle of 3 kids, has more than 50 cousins. Big extended family. Never broke a bone. And here she is, Cozy. Everybody, please give a warm round of applause for our Student of the Week, Cozy. Oh, I don't know how to say her last name, Cozy. Najee, maybe? I think it's sweet that she has an NN. I don't know if I've ever seen a name with NN. I like that. So Cozy's our Student of the Week. So give her pay respects to the Student of the Week. Please bow in her presence. And she has. I should have announced it on Monday, so she might have a short week. But okay. Our SO2W this week, Cozy. All right. Any questions before I start teaching you more stuff? I'm checking the chat here. No, Carly asked, do honor students have different exams? They do not. Honor students just have the honors projects. I think in the past I've said on the homework, I'll give like on homework, the first one I'll say, oh, there's questions 7A, B, and C. And I tell everybody, oh, you can just do like one of the three or all three. I think in the past I've said, okay, honors students do them all. But then a lot of times they just do them all anyways, but I don't know. If I don't, yeah, that doesn't matter to me. The main, pretty much the full thing the honor student has to do is the tryout and then the assignments, those Google slide animations. Okay, so let's start. We left off step by step again. Oh, about two of those now. Our chapter outcomes. And my intros, they're always super long. This intro we just finished at the beginning of the semester, there's a lot of things to get going, but they'll get shorter. Okay, so here we are. So now we learned about some curved arrow mechanisms. We're going to get a lot more practice of that over the year. And now we're on to outcome 7 here. Understand a hydrogen atom described as a neutral, a proton, or a hydride ion. So here it is. I'll do some examples on the Jamboard, but let me first say this. So a hydrogen atom just has a single proton. If you have if you're an atom with one proton, you're a hydrogen atom. If you have 2 protons, now you're a whole nother atom. You're helium. 3 lithium. I should know this. Yeah, lithium. 4 protons, you're beryllium. That's how you figure out. Atoms are defined by the number of protons. And then the neutral hydrogen atom has that one positive proton, no neutrons, just one proton. And it has a single negative electron. So overall, no charge, plus proton, negative neutron. And then the hydride, it has an extra electron. So it winds up having a negative charge because it's like -2 + 1 -1. So we call this a hydride when it has an extra electron, just a hydrogen atom when it's neutral. And then if you lose the electron from the hydrogen atom, it's just a proton, that's it. It's kind of weird, huh? All the other atoms, when you lose an electron, they still have other electrons in that nucleus. But when you lose the electron of a hydrogen atom, it's just a proton. So that's why when we describe acid-base chemistry in terms of the Bronsted acid-base chemistry, we talk about deprotonation and protonation. So let me show you some examples of that. Jamboard here. I'll do the protonation. Okay, so let's go with an acid. I'll do a really strong acid. This is sulfuric acid. So you might not be as familiar at seeing sulfuric acid as a Lewis structure. You're probably more used to seeing it as H2SO4, but you see that's the same formula for this. My hand is sloppy. H2SO4. Okay, so I got that, and then I'm going to show. I'll use water to be the base here, and notice my colors I'm using. Okay, so what's going to happen when water reacts with sulfuric acid? It reaches out a lone pair of electrons, and I'm touching the lone pair, and I'm touching the hydrogen. It's going to take what part of that hydrogen? So this hydrogen here is a proton, a positive proton, right? And then it has a negative electron, and then there's another negative electron. That's the sulfurous electron. So these two are the bond, right? And this here is the hydrogen nucleus. Okay, so when this water reaches its lone pair out, is it getting any of the 2 electrons in the bond? Oh, I should finish the reaction to show you the products here. This is very product favored. Ugh. Yeah. So what is this water molecule taking? Is it taking the proton of the hydrogen? You can answer in the chat for me. So in this mechanism that I'm drawing here, is the water molecule, is it getting the proton? Is it getting the proton of the hydrogen? Yes or no? It's just taking the proton. So it's only taking the proton of the hydrogen because the 2 electrons, these 2 electrons, these blue ones, one from the hydrogen, one from the sulfur, they're both going over to the sulfur. Or not the sulfur. Oh, I got that wrong. This is oxygen. Huh? Sorry. So that's the bond, right? The rest of it, SO. Okay, so the sulfur is getting both electrons. One of them I think of as belonging to coming from the oxygen initially, and then the other one's with the hydrogen atom. So the yep. So this and the sulfuric acid, oxygen of is deprotonated, we say. Just loses a proton. It keeps the 2 electrons. So the sulfuric acid is deprotonated. The water, on the other hand, it is just taking the proton of the hydrogen. We say it is protonated. And these reactions, these acid-base reactions, this type of acid-base reaction, would you have like a proton donor, proton acceptor? We call these reactions acid-base reaction. So transfer. The proton was transferred from the sulfuric acid to the water which is now hydronium. And this is also this is a Bronsted acid-base reaction. Does anybody know what that means? So Bronsted acid-base reaction. I'm not sure if your chemistry, your general chem class went over that. In a Bronsted acid-base reaction, the acid is called a proton donor. So the sulfuric acid is donating a proton, and the base is referred to as a proton acceptor. OR, AR? I don't know. Acceptor. OR. I don't know this well. So this is a Bronsted acid base reaction, or sometimes people refer to it as Bronsted-Lowry. Those two names get credit for. All right, so that's an acid base reaction, and that's why I want you to understand that like this is called just the nucleus of a hydrogen. It's just a proton when it's a positive charge is what it's called. Okay. I'll do a hydride reaction later in the semester. We'll learn some reaction with hydrides. All right, and now one of the concepts we'll use a lot in this class is electronegativity. So I feel pretty confident you heard about that in general chem, and it's not too difficult of a concept. It just means it describes when two different atoms are bonded, covalently bonded. One of them might hog the electrons towards it more, and if it does, it's called the more electronegative atom. So here's our Ocam periodic trends animation I made up. So this has a lot of trends we'll be talking about throughout the semester, but I'll just focus on the electronegativity first. So I'll do size as well. So in terms of size of atoms, they're how far out from the nucleus their valence electrons go. The atoms get larger pretty much. There's some slight exceptions along the way. They get larger as you go to the left of the periodic table. So for instance, what do you think is a larger atom? Fluorine or boron? What's larger? Tell me in the chat, fluorine or boron? Yep, boron's larger. And you can get boron in Boron, California. As you drive down the 5, you go through Boron, California, where they have boron mines. Okay, and then what about as we go down the periodic table, you get larger, and also the change in size is more extreme. So the difference in size between say fluorine and chlorine is a lot bigger than say fluorine and oxygen. It's a small change in size along the periodic table, but a large change each row down the periodic table. Because as you go down, you go up another quantum number, if you remember that, like the valence electrons of carbon, nitrogen, oxygen, fluorine. It's the 2s, 2p. Those are the valence. When you come into here, now you're 3s, 3p, and you got the here's where we get the d's. But okay. So size. Now the next important one that I brought us here is electronegativity. Atoms become more electronegative as they get closer to fluorine. So as you go to the right, you're more electronegative. So what's more electronegative, carbon or nitrogen? Yeah, nitrogen's more electronegative. And electronegativity increases up the periodic table as well. So this trend is just opposite of size, huh? And so fluorine is considered the most electronegative atom. That means if fluorine's bonded to any other atom, it's going to hog the electrons to it. It's going to have more of them. It's not going to share equally. And then there's, Bronsted base strength. That's something we just learned about. Bronsted's means base is a proton acceptor. We have this trend, which I'm going to go through these last ones really quick. I'll just nucleophilicity we'll talk about later. Polarizability later. Bronsted acid. Okay, skip that for now. So the main thing I want you to know, which you probably already knew, fluorine is the most electronegative atom. Okay, ionic and covalent bonding. Let's do that one now. Alert this settings. Are you guys seeing my alert? Okay. Let's do this one real quick. So some chapter 1 outcomes, we're continuing on here. So electronegativity, we got that one. And then the main difference between ionic and covalent bonding. So ionic bonding is not sharing of electrons. Just an attraction between opposite charges. So just a second, Josephine. And then not sharing of electrons, just ionic attraction. So an example of an ionic bond would be, sorry, I'm waiting on my waiting on the iPad. Come on, iPad, let's go. We can do this. We have the technology. There we go. Okay. So an example of an ionic bond would be sodium and chloride. So sodium and chloride have a big difference in electronegativity. So that means the chloride doesn't want to really share electrons with the sodium. It just wants to take them all and hold them all. And it'll have a negative charge. Sodium has a positive charge, and they're attracted just because they're opposite charges. Big. Okay, it's a big difference. And actually, you can look up electronegativity trends, like if you go to tables. Yeah, here's a table of electronegativities. So for example, the value for chlorine electronegativity is 3.16, where sodium is 0.93. So chlorine is much more electronegative. So they don't want to share their electrons. They're two different in electronegativity. And these electronegativity values, they're just averages, approximations. They aren't exact. You can look up a number of electronegativity tables, and the values will all be slightly different because it depends on the chemists who made up the table, like what kind of research they did. They're kind of biased by the molecules they work with. Okay, so that's that. And then covalent bonding, on the other hand, is the sharing of electrons. So it's not about being attracted because of different charges. It's you're actually sharing electrons. So in covalent bonding, do you think you need molecules to have the same electronegativity? I mean, similar electronegativities or different electronegativities? Yeah, I'll show you an example. So here's an example of a covalent bonding, like the carbon-hydrogen bond. So are the electronegativities similar between carbon? Yeah, good. Are they similar between carbon and hydrogen? So carbon's listed at 2.55, hydrogen is listed at 2.2. So yep, pretty close, right? And this carbon, you'll see in my future assignments, that carbon is just an average of the different types of carbon. I don't really feel like that even applies to this carbon. Well, so similar. So you can talk about extremes between ionic bonding and covalent bonding. But actually, before I do that, so Josephine, you had a question. Is it something quick, or okay, go ahead if you have it. It's a quick one. Well, if you want to ask, you could type it in the thread. All right, so ionic bonds are the extreme. Ionic bonds are just the not sharing at all. Like a pure ionic bond would be no sharing at all. And a pure covalent bond would be a total equal sharing. But in reality, ionic bonds, actually, they do share a little bit. So they're part covalent, but mostly ionic. Okay, Josephine, let me try to answer that after lecture if you're around. And then covalent bonds, though, they can be pure covalent bonds. So let's look at that. Let's go to a pure covalent bond. Equal sharing. Can anyone tell me, suggest a bond that's equal sharing of electrons? Think of an example. There we go. Yep, now we're seeing it. You just need to have two of the same atoms. You got the right idea. So this is hydrogen will work. Oxygen will work. Nitrogen. Yeah, these are all examples of that because the same atoms My phone just rang as a spam call. Did you guys hear that ring? It was in my headphones. Now I guess you wouldn't. I always get spam calls right about this time of day. So annoying. Same atoms bonded. So they have the same electronegativity. And share electrons equally. So you can say that they are purely covalent bonds. Okay, and then there's the in between pure ionic, pure covalent. There's the polar covalent. Polar covalent is part ionic covalent. So part ionic meaning it's attracted from positive and negative charges, and part covalent because it's attracted between positive and covalent because it's sharing. Sorry. Okay, so the next an example of this, I'll show you what's considered by many the strongest covalent bond. It's mostly covalent. The silicon-fluorine bond. So that bond right there. Single bond. I say single bond, like for example, this hydrogen up here, it has a single bond. The oxygen has a double and the nitrogen has a triple. So the more bonds you have, the stronger, it's harder it is to break the atoms apart. So this single bond is the strongest, just single bond. It's like much stronger than a hydrogen-hydrogen bond, but it's not going to be as strong as a triple bonded nitrogen. That would take more energy to break. So why, let's describe this a little bit. It turns out that the fluorine and the silicon don't have the same electronegativity. They're different atoms, different electronegativities. So in terms of fluorine is what? On this table, they list fluorine as 3.98. 3.98. And then the silicon is listed at under carbon 1.9. So they're not too close. Fluorine's about double. So the bond between silicon and fluorine, those two electrons, are they going to be more on the fluorine side or more on the silicon side? More on the fluorine side. So we can think of it as the fluorine is more electronegative. It hogs the electrons to it, giving, give it a partial negative charge, because electrons are negative, so the fluorine has extra electrons. It's going to be partial negative. And we draw partial negative charges a certain way. We use the symbol delta, lowercase delta. So partial negative charge. Oh, sorry, that didn't come out very pretty. We represent that with a delta negative. So what I'll do is I'll come over to my structure and I'll say, oh yeah, that fluorine's hogging all these electrons. It's going to have a delta minus charge, partial negative charge. What about the silicon? Would it have a charge, do you think? Yep. Obviously, I'll make it in blue. I like to represent positive as blue. Silicon's going to be partial positive. So the thing that makes the silicon fluorine bond so strong is that there's some covalent bonding that holds it together, sharing of electrons. And there's also ionic bonding. The delta negative of the fluorine is attracted to the delta positive of the sulfur. STER. Sharing of electrons. So it's part covalent, sharing of electrons, and part ionic. Attraction between the partial charges, partial opposite charges. Okay. And most covalent bonds are in this polar covalent category, where they're not equally shared. And whether something is more ionic bonded or more covalently bonded, it's there's just like an arbitrary decision on that. So let's see if we can find it. It's like the difference in electronegativity is over 1.8 or something like that. I forget. Yeah, here's one person's opinion of it. You don't have to memorize this. I just want you to have the concept that bonds can be ionic or covalent, and they're usually a little of both. So if the difference in electronegativity between two atoms is only like 0.5, then we say it's actually, we consider it most just non-polar covalent. Like it's not, no one atom's really hogging the electrons to it much. But if it's between 0.5 and 2.1, then we say it's polar covalent, like the fluorine silicon. And if it's greater than 2.1, the big difference in electronegativity, we say, oh, that's just a straight ionic bond. Okay. Now, so state there's ionic covalent bonding, extremes, understand that. Okay, breaking a bond and making a bond. So this is sort of a, well, actually, let me see. Let's do this last outcome and then we'll take a break. So this can be confusing for a lot of students, especially if you've had biology. In biology, they tend to state this in a way that seems like they tend to talk about this subject in a way that seems opposite of what I'm saying. But this is the way I believe it is. And I can try to, if you're confused about the way your biology definition works, I can show you how they're compatible. So the way I want you to know this is that it takes energy to break bonds. And when bonds form, it releases energy. So for instance, if you, I'll write up examples. So, okay, so I'm going to break a bond first. Let's look at one of the first reactions we're going to learn soon is it's called the radical halogenation of alkanes. Long name, radical halogenation of an alkane. The first step in the mechanism involves bromine breaking apart into radicals. So you'll notice I'm using these half arrows or fishhook arrows because only one electron is going one way and one the other. So when a bromine breaks apart like this, makes two bromine radicals. They have an unpaired electron like that. So we broke the bromine bond in this reaction. Does this reaction take energy or does it release energy? Tell me in the chat, please. Takes energy. And we're going to see this is caused by, we add energy in the form of light. We're going to start these reactions with shining light on them. Okay, so takes energy to break a bond. That definition seems easy to remember because those two atoms are being held together and you have to like rip them apart, right? So I think I got to pull them apart. So it's not too bad there. It's the making of bonds that a lot of times confuses people. So let me do an example of that. So I'm going to take one of these bromines. And I'm going to have it react with the hydrogen off of a carbon. I'll just do methane. It's covalent here. Okay, so the way I'm going to show the curved arrow mechanism is one of the red electrons is going to meet one of the blue electrons in the middle like this, and we're all touching. And then, boom, and then that bond goes there. And what we wind up with is a bromine with the hydrogen. Now that this one's I'm gonna have to do this one with two colors, because there's like one electron from the blue bromine electron, one electron from the red hydrogen electron. There it is. And then the methane there that reacted has a single red electron on it like that. Okay, so this is how I want us to think about it. This carbon-hydrogen bond, is it broken or forming right now? It's broken. So does that take energy or release energy? Takes energy. Over here, though, we have a bond forming. So does that take energy or release energy? That releases energy. That's the one that's kind of weird. Releases. I can't, all of a sudden I can't spell release. Yeah, releases energy. Okay, so we have in this one reaction step, we have a broken bond that's taking energy to break it, but then we're releasing energy when the bromine hydrogen bond forms. Okay, so but overall, we decide, oh, which one's more energy or less energy. Overall, this step takes energy. So if this step takes energy, what does that mean in terms of the bond strengths? What's the stronger bond? Which bond? So if it takes energy overall, does it take more energy to break this bond than is released when the bond forms, the new bond forms? Yeah. Takes more energy to break the HC bond than is released when the RH. That's why it's overall takes energy to have this step occur. We say this step is what? Endothermic or exothermic? Does anybody remember that step? Yeah, and in the beginning, it's endothermic, yes. In the beginning, I said that a lot of times people get confused with the definition, with these kind of definitions when they relate it to biology, their biology studies. Because in biology, a lot of times the teacher will say, oh, we're going to break down fats to get energy. We're going to break down carbohydrates to get energy. And it is true when you, in your body, when you break down, say, sugar, a carbohydrate, when you break down that sugar in your body, you're breaking the bonds, but you're not getting energy when you're breaking the bonds. It actually takes energy to break apart the sugar in your body. But then the product of that reaction is involves carbon dioxide. So when we break down a sugar, eventually we produce carbon dioxide, and the carbon dioxide bonds are really strong and they release a lot of energy. So the energy it took to break down the carbohydrates was not as much as what was released when CO2 was formed. And so that's why it's an overall energy gaining process for us. But then it just seems counterintuitive, but you don't think about the energy released for CO2. You just say, oh yeah, I broke down those fats and carbohydrates and I got energy. You did, but it was from the CO2 releasing the energy. And then we exhale CO2 and it shows up on our IR. Okay, so we got that one. Let's see where we're at. Energy. Okay, formal charges. I'm not going to do that now because I did it in lab and it's part of the secret hydrogens calculations. I think you're good with that. And the octet rule, I'll start with that one right after a break, actually. This one, this one was a long one. I forgot. I made this one up over the summer too. Yeah, I'll just do some examples. So you have these examples to work through. I don't believe I have a quiz for this one. I think I just put this one as part of the homework. Yeah. Cool. So tets charges. We don't get into hybridization. Looking good here, huh? So the octet rule is basically this trend that we find that atoms, they tend to be most stable when they have an octet or 8 electrons around them and around their valence. So in practice, we'll look at, like, I'll just start drawing up some example molecules. Let's look at like a carbonate. Do you guys remember that one? CO3 2 minus might have been one of the ones you had to memorize in general chem. So carbonate's Lewis structure, one of them you could draw like this. Has -2 overall charge, and you can see it in this Lewis structure. I've got a -1 adds up to -2. Okay, so let's calculate the octet of these atoms. So the formula I like for octet counting is just to count up the bonds, or no, it's 2 times the bonds, 2 times bonds plus electrons, like lone electrons. So that's my octet formula. It's slightly different than the formal charge formula. Remember, the formal charge formula is group number minus bonds, not 2 times the bonds, just number of total bonds, minus electrons. And I don't like the way I put 2 times there, 2 multiplied by the bonds. Okay, so let's calculate some octets for this molecule. So if I go to this oxygen here, its octet is, how many bonds does it have? Chat, can you tell me in the chat how many bonds does oxygen have? Yes, 2 bonds. It has it's a double bond. It has a sigma bond and a pi bond. We'll go into more details on that shortly too. And how many lone electrons does it have? 4 electrons. Okay, so what is 2 times 2 is 4 plus 4 electrons? How many electrons does it have around it? 8. It's an octet. And when it has an octet, it's happy, it's low in energy, it's not as reactive. Okay, and then what about this carbon? Let's do it. Let's go. It's octet count. So 2 times how many bonds does it have? It has 4 bonds. Yep. 1, 2, 3, 4 bonds. plus how many lone electrons? 0 electrons. So what's its count? 8. It's got an octet too. It's happy. Yay. What about the oxygens with a negative formal charge on them? How many bonds do they have? One bond. Plus how many lone electrons? 6 electrons. So does it have an octet? Yes. Got it. They're all happy. Got octets. As you do this over and over, and hopefully maybe you're already there, you don't even need to use your formula, like, because you just kind of do it in your head. You just know, okay, bonds are counted as 1. So I just kind of go like a 1, 2, and electrons are each 1. So 1, 2, 3, 4, 5, 6. Done. Or you even go faster, you just count by 2s. So each bond is worth, oh, I'm sorry. I did that wrong. I said 6. So each bond is 2 electrons. So I go 2, 4, 5, 6, 7, 8. Or I can just go 2, 4, 6, 8. Let me do this one. 2, 4, 6, 8. We got it. Okay, and octets are good because they help you with predicting reactivity, things like that. So let me show you an example of it. So if I have a boron trifluoride, it's an interesting molecule. Boron trifluoride. Does this fluorine have an octet? I'm going to do it the fast way. 2, 4, 6, 8. Yes, octet. Got it. Does the boron have an octet? Let's see. 2, 4, 6. No octet. It's short in octet, which makes it reactive. And one of the ways it likes to react is it can add another fluorine. So if you have a fluoride anion, oh, does that fluoride have an octet? 2, 4, 6, 8. Yes. So the fluoride can come and it can add to the boron. And it makes boron tetrafluoride. Actually, there's probably a better way to name that. Oh, that's right. And when the fluoride adds, it gives the boron a negative charge. But so the boron's, it's real, it's never happy. Initially, it had no octet, which made it reactive over here. I got no octet. It's kind of whiny. I got no octet. Adds the fluorine, adds the fluoride. And now, does it have an octet? 2, 4, 6, 8. Yes, it has an octet. So that's a way you can say yes. So that's why you can say yes. It's you should be happy, boron. Now you have an octet. You were complaining you didn't have an octet. Now you got an octet. But then what does the boron say? But I got a negative charge. It gets a negative formal charge, so it's never happy. The fluorine can come back off, and now it's like, oh, no more negative charge. Boron, you happy? I don't have an octet. So we'll use octets to help us predict reactivity and things like this. All right, so we got octets. Calculating octets and formal charges. You're going to get a lot more practice with that. Oh, and then I want to talk about the octet rule. This is often confused by students. So what is the octet rule? The octet rule is basically, for us, it's just, well, for everybody actually, it's just one row of the periodic table. Can't have over 8 electrons. They can have under, but they can't have over. All right, let me show you what I mean. So all we're mentioning here is this row. So these atoms right here follow just these ones. So it's just those atoms that follow the octet rule. The next row down, like sodium, magnesium, aluminum, silicon, they don't have to follow the octet rule. They tend to have octets, but they don't have to. They can actually, this row, for instance, these atoms right here, they have the 18 electron rule, not the octet rule, because so they can have up to 18 electrons around in their valence because they have d orbitals. You start filling in those d orbitals, not just the s and the p orbitals. All right, so when we talk about the octet rule, it only things we're going to mostly be looking at is like boron, carbon, nitrogen, oxygen, fluorine. That's about it. And the octet rule says you can't have more than 8 electrons, but you can't have less. So let's look at some examples. Is this breaking the octet rule? If I have a carbon that has 3 bonds and a positive charge, is that breaking the octet rule? In the chat, answer me, please. Is this carbon right here breaking the octet rule? Yes or no? Is it breaking the rule? No. No. Breaking the octet rule? No. Reactive. Less. But it's not breaking any rules. These molecules do exist, and we're going to work a lot with them. They're called carbocations. All right, what about if I have this situation? 1, 2, 3, 4, 5, 6. Is this guy breaking the octet rule? Yes or no? Yes. Has an octet count of 2, 4, 6, 8, 10, huh? Over 8. Octet rule. I'll show the calculation real quick for that one. So the octet count for that one is, it's got 2 times 5 bonds. Oh, come on. 2 times 5 bonds. Oh my goodness. Trying to rush this. 2 times 5 bonds plus 0 electrons. That's 10. Too many. A couple more that we see a lot. Yeah, the second row of the periodic table, Sajin's asking, is this the expanded octet? Yes, that's another term that you use to talk about that. Okay, 2 more quick ones. No, I don't do that. And this is phosphoric acid. Okay, so are we breaking the octet here on this carbon? And for the phosphorus. So are we breaking these octets? So for the carbon, the answer is yes, because the octet count for this guy is 2 times 4 bonds plus 1 electron. That's 9. It's over, broken. For the phosphorus, though, what's its octet count? Its octet count is, how many bonds does it have? 2 times 5 bonds plus 0 electrons. Is that breaking the octet? That's 10. Is that breaking the octet rule? I see some yeses and some nos for this one. So I'm asking, is it breaking the octet? I shouldn't say, I gotta be more specific on my question. Let me fix this. Oh, come on. Edit. Are these breaking the octet? Yeah. So the carbon, we said yes, it was. But the phosphorus, is it breaking the octet rule? No. It's not breaking the octet rule because it does not have to follow it. It has the 18 electron rule. It's lower on the periodic table. Okay, so that's fine to draw. But this is not good to draw, the breaking the octet rule. It doesn't exist. And if we go back one slide, you can see, yeah, phosphorus is under nitrogen. Doesn't have to follow the octet rule. All right, cool. We're doing good. Let's see, where are we at now? We got the octets. So you know what? I think I'll save hybrids for next lecture. Yeah, we'll get there. I think next lecture we got hybrids, Lewis structures, geometry, dipoles. Yeah, this stuff just takes a little while. Chapter 1 is a long one now. I've added a lot in the past. I have other material, like some of this material I've had in other chapters, but I just want to, chapter 1's kind of mainly like a general chem review, looking at it from an organic chemist's perspective. So we're getting there. So I think I'll pick up at hybrids next time.